All right, this problem is from chapter 27. It's number 6, and it reads, two parallel slits are illuminated by light composed of two wavelengths. One wavelength is 645 nanometers. The other wavelength is just known as lambda b and is unknown. On a viewing screen, the light with wavelength 645 nanometers produces its third order bright fringe. At the same place where the light with wavelength lambda b produces its fourth dark fringe. The fringes are counted relative to the central or zeroth order bright fringe. What is the unknown wavelength? So, a little bit of reasoning behind this. Each wave produces an interference pattern independently of the other wave. So, since the waves have different wavelengths, the positions of their bright and dark fringes will also be different. Using the conditions of interference, we can express the positions in terms of the wavelength and the order of the fringes. And when we set the positions of the fringes equal, we'll obtain the equation, which gives us the unknown wavelengths. Sounds a little complicated, but let's dive right into it. So, first thing first, knowns and unknowns. So, data for the problem is all on the table. So, the wavelength of wave 1 is 645 nanometers. The order of dark fringe of wave 1 is 2. The order of the bright fringe of wave 2 is 4. The separation between this list is unknown, and the wavelength of wave 2 is what we're looking for. The direction to the mth order bright fringe is described by this expression sine of theta equals m times lambda over d, and for the dark fringe, sine of theta equals m plus 1/2 times lambda over d. So when we substitute the numerical values, we're able to find that lambda 2 equals 2 plus 1/2 times the original wavelength, which is 645 over 4, which is the order of the bright fringe of wave 2. So that equals 403 nanometers. So that right there is how you find the unknown wavelength when you're given one wavelength and order of dark and bright fringes for the other. I hope that was clear. Have a great day.